For those of you who are online, I'm sorry it was muted. So we will start with the first talk, which is by Antoine Jego from Vienna, who's going to talk about the Brownian loop soup and Liouville measure. So Antoine, please.
Okay, so thank you very much. I will start by showing my screen. Okay, so you should be able to see my screen now. Okay, so thanks a lot. Thanks for the invitation. It's a great pleasure to speak here today. And I will talk about multiplicative chaos of the Brownian loop soup. And this is joint work with Elia Decon, Nathaniel Verestiki, and Titus Lepu. So I will start by introducing Brownian loop soup. And so we'll see that this work is mainly about a relationship between two objects, Brownian loop soup and Liouville measure. And so we'll start by introducing these two objects. So the first one is Brownian loop soup. So this is an infinite collection of Brownian-like loops. So this is a bit like depicted on the right-hand side if you want. And more precisely, it is a Poisson point process with an intensity which is given by theta times a loop measure. And so here, theta is a positive parameter. And the loop measure is some infinite measure that I'm not going to describe more thoroughly. But this was introduced by Lawler and Werner in 2004, I think. I'm not so sure. And it has connections with many different objects in random conformal geometry. And here's a simulation of Brownian loop soup. So I think what we can see here is loops that have a diameter larger than a given threshold. So otherwise, without this this cutoff, we would not see anything. We would only see a completely black picture. And so now I want to argue that theta equals a half is a spatial point. So remember, theta is this parameter that we have in the intensity measure. And so indeed, if we look at the clusters of loops, meaning that we look at all these chains of intersecting loops, then we see that there is two regimes. There are two regimes. The first one is when theta is smaller than a half, smaller or equal than a half. It turns out that there are infinitely many clusters. And in that case, the outer boundary of the outermost clusters form what's called a conformal loop ensemble. Whereas if theta is strictly larger than a half, then there is only one cluster. So from this perspective, theta equals a half is a very special point. There is another reason why theta a half is special, which is that at that specific point, there is an isomorphism between so the occupation field of the loop soup and half of the GFF squared. So the occupation field, this is a field that measures how much the loop soup spent in a given region. And the GFF is, so the GFF is the Gaussian free field. And I'm going to explain in more detail what this is. So here is the simulation of the GFF. So this is so we can think of the GFF as a random height function, and it appears in many different contexts. So it is the universal scaling limit, for instance, of the height function in dimers, and also of the characteristic polynomial of large random matrices. And informally, what the GFF is the following. So we have a given region of the plane, so a given domain D, and the GFF is a random function indexed by the points of the domain, which is distributed like this. So it is a Gaussian, and the covariance is given by the green function of the Laplacian. But it turns out that the green function in 2 dimensions blows up logarithmically on the diagonal. And so because of that, the GFF is actually not defined pointwise. Instead, it is rigorously well defined as a random generalized function. So this is a bit what we saw in the previous picture. So we had a very rough object with a lot of spikes, if you want. Okay, so that's the GFF. And now I want to introduce, if you want, the second main character of the story, which is a Liouville measure. So Liouville measure is a random measure, which is formally defined as the exponential of gamma times the GFF. And so here gamma is a parameter, which is between 0 and 2. And so, okay, so taking the exponential of a generalized function is a priori not a well-defined operation. But it turns out that we can make sense of this measure in this range of parameter. And this is a special instance of what's called Gaussian multiplicative chaos measures. And these measures, they pop up in many different areas of mathematics. So for instance, in number theory with Riemann zeta function, again, random matrices, finance, planar Brownian motion. So this will play a crucial role in the work that I present today. And also, so Liouville measure is actually quite special because it can be seen as being the volume form of a surface chosen uniformly at random. So in that case, you have to choose the parameter gamma to be equal to square root of 8/3. Okay, so that's Liouville measure, and so here are so 3 simulations of it for the same underlying Gaussian free field and 3 different values of gamma. So what is depicted here is, if you want, the density of the measure with respect to Lebesgue measure. So although Liouville measure does not have a density with respect to Lebesgue measure, if it had, it would look like that. And so in particular, we see that as gamma approaches the critical value 2, the measure becomes more and more supported on fewer and fewer points until it degenerates to 0. Okay, so that's it about Liouville measure. So far I introduced 2 objects, Brownian loop soup, okay, maybe 3, Brownian loop soup, Gaussian free field, and Liouville measure. And so our work with Eli, Nathanael, and Titus. So this work appeared this morning on the archive. So our work is basically, the goal of this work is to understand the relationship between these objects. And more specifically, recall that we have this Legendre isomorphism that tells us that the occupation field of the loop soup, so that we have here at criticality, so when theta is equal to 1/2, is distributed like 1/2 of the GFF squared. So we can couple these 2 guys such that this relation holds. And so the type of question that we want to understand in this work is, if I sample a point according to Liouville measure, so my point Z here, what does the loop soup look like near such a point? That's the type of question that we want to understand. So more precisely, so now I want to explain a bit more what we could expect. So Liouville measure is supported on points that are called thick points. So these points are very atypical in the sense that the field, so the underlying GFF H, is atypically large at these points. And so in view of Legendre isomorphism, if H is large, then the square of H is going to be very large as well. And so the local time, so the occupation field of my Brownian loop soup will be very large as well. So the question that we want to understand is basically how is it possible? So how does the loop soup create a thick local time at a given point like this? So thick local time really means that there is a lot of accumulations near that point. So there are different possible scenarios. So for instance, we could have very few loops that visit such a point, but each of these loops will be very thick, will visit this point unusually often. Another possibility, which is this one here, is that we would have many loops, but with a fairly typical local time. And so it turns out that the correct answer is intermediate. We have infinitely many loops that are all thick, and moreover, we can describe the respective thickness of each of these loops. So if I denote A1, A2, etc., the thicknesses of my loops, then we show that they are distributed as a Poisson-Dirichlet distribution with parameter theta. So in this context, theta was equal to half so far. So what this means, a Poisson-Dirichlet distribution. So we have a random partition of A. So A is actually equal to gamma square over 2. So gamma was the GMC parameter. Remember that Liouville measure is the exponential of gamma times h. And so we have a random partition of A. And so this is Poisson-Dirichlet distribution. And a way to understand this distribution is as follows. So this is known as the stick breaking procedure. So here you look at a random partition of 1, and you are going to select a portion of your stick which is distributed as a beta distribution with parameter 1 and theta. So when theta is equal to 1, this is just uniform. And then you iterate. So this means that this is going to be one of your values here, and then you iterate this procedure on a smaller portion of your stick. So you start again here with the beta distribution in that interval, and so on. So that's the Poisson-Dirichlet distribution. And more generally, actually, our work is not at all restricted to the critical case theta equals a half. And so in order to make sense of such questions, we need to generalize the notion of Liouville measure to any intensity theta. And so this takes a big portion of the article. So to do that, we first we don't really consider Liouville measure, but we actually consider an unsigned version of it, meaning that we take unsigned because in Legendre isomorphism we were taking the Gaussian field squared. So Legendre isomorphism doesn't really see the sign of the GFF. So that's why we consider an unsigned version of it. And so we take the exponential actually of gamma times the GFF. And since and it turns out that this measure is actually the sum of two Liouville measures with opposite parameters. So this is just because so of course, if the field H was well defined pointwise, then this identity would not hold. But because the field takes atypically large value under this measure, we have either a very large positive value or a very large negative value. And so in view of Legendre isomorphism, we can rewrite informally this unsigned measure as follows. So we exponentiate gamma times the square root of the local time of our loops. And so what we show in our paper is that for any gamma and any theta, we construct such a measure. So here, the intensity of the loop soup is not restricted to theta equals a half anymore. And we do this both in the continuum, so directly from the continuum and from the discrete. Okay, thank you very much.
Okay, thank you very much. So we have time for a question or two, if there are any from the audience. So I think online we didn't have any questions so far. So if not, okay, it seems there are no questions. So in that case, let us move on. I think we can move straight away on to our next speaker, who is on site. That would be Alex Bols from the University of Copenhagen, who will talk about the absolutely continuous edge spectrum of Hall insulators on the lattice. So you need to get your slides.
Right, let me first try to find my slides indeed. They should be on the desktop, so I will make this a little bit smaller and click on this. And then if I do Control L, this should happen, very good. And to move slides, I could press these buttons perhaps. Yes, that is right. Okay. I can take off the mask to speak, I presume.
Yeah, sure. Just like make sure if the Zoom can hear us. It's this one. Oh yeah, great.
Very good. So hello everybody, I am Alex and I will talk to you about continuous edge spectrum of Hall insulators. And I would first like to thank the organizers for giving me this opportunity. It's very nice once again to speak in front of an audience in the flesh. Okay, so let's get started. So let me first also mention this is joint work with Albert Werner, who just as myself is also at the University of Copenhagen. It's not moving. Aha, there we go. So, right, I will first quickly repeat again what the Hall effect actually is. I think most of you just heard the talk by Marcello Porta, so I can be brief, I think. And then sort of, I will try to convince you that if you have a Hall insulator with an edge, then something special has to happen at this edge, namely there have to be edge currents, and these edge currents have to be associated to absolutely continuous edge spectrum of the Hamiltonian describing that Hall insulator with an edge. And fine, so I will convince you of this fact sort of in a very physicsy way. And then at the end I will state a theorem that sort of mathematically states what I have tried to convince you of physically. And if there is time, which there probably won't be, I will also sketch briefly the proof of the theorem, which doesn't quite follow the physics story, but I think the physics story is just a lot nicer than the proof of the theorem. So let's get started. Right, so what is a Hall insulator? A Hall insulator is a two-dimensional, a flat material, and it is an insulator in the sense that if you apply an electric field to it, then there won't be a current in the direction of the electric field. But there is a Hall current perpendicular to the electric field, as shown in the picture. And as usual in sort of currents in responses to driving fields, the Hall current in response to the electric field is in fact in strength proportional to the applied electric field, and this proportionality constant here denoted by sigma is called the Hall conductance. And what is very special about it is that if you measure it at low temperatures, then this Hall conductance is precisely quantized in multiples of some universal constant, which happens to be given by the square of the charge of an electron divided by h, Planck's constant. Okay, so now I will try to convince you that if I have such a material with that property, then something, and I give that material an edge, so it's not an infinite plane as mathematicians sometimes like, but it's a finite piece of material depicted here, then something special has to happen at the edge. So we imagine that we have such a finite piece of Hall insulator described where the motion of the electrons in the material is described by a single particle Hamiltonian, which we call H. And now we will do something. We will start driving a Hall current in the bulk by applying an electric field. But I will now insist that this electric field is derived from an electrostatic potential V, and I will model the new situation applying the electric field simply by adding this electrostatic potential to the Hamiltonian H. Right, so as said before, what will happen in the bulk of this material is that of course, there will be a Hall current perpendicular to the electric field. So look quickly at this picture. So the electric field is, of course, the gradient of the potential, and these red lines are the equipotential lines. So the electric field is perpendicular to these equipotential lines. The Hall current being perpendicular to the electric field, it will flow actually along the equipotential lines of the applied electrostatic potential. Now, that's what I just said. Now, of course, now let's look at this picture a bit more. Right, so I add this potential to the Hamiltonian, and I do very much a thought experiment. I let the system equilibrate completely, and yet still there is this Hall current in the bulk. But of course, a system at equilibrium, it cannot build up charge anywhere. So this picture cannot be complete because there is a Hall current colliding into the boundary up there, and if nothing happens there, charge will build up there, and that is impossible in an equilibrium situation. So, of course, what has to happen is that there must be some mechanism to get rid of the charge that flows from the bulk to the boundary, and let's think a bit about what should happen precisely. So, let's take an arbitrary curve C connecting 2 points of the boundary. Then I know there is a bulk Hall current flowing through this curve given by this formula, right? I just integrate the Hall current across this curve. The Hall current is proportional to the electric field, which is the gradient of the potential, proportional to the Hall conductance. And I find that the bulk current flowing through this curve C is given by a difference of basically a difference of the potentials at these two endpoints A and B. So how can we fix the problem of a would-be charge buildup at this boundary? Well, we can fix the problem if merely by the existence of a charge at a point on the boundary, this charge will automatically move away with the speed corresponding to an edge current given precisely by the value of the external potential at the boundary. Right, so if you then add this current to the previous equation, you will see that again there will be no charge building up anywhere in the insulator, which is the situation that we want. Right, so the existence of such an edge conductance would solve our problem. Now we could think a bit about possible mechanisms for how such an edge current could exist in such a system. So to do that, what I have drawn here is the horizontal axis is this curve C from before, and the dots are electron states that approximately have an energy given by the vertical scale and are also approximately localized along the curve as shown in the picture. And if there is no external potential in the top of the picture, then all the states up to a certain Fermi energy are filled, and that is the situation without the perturbing potential, and also no currents flowing in the bulk. But then when we apply the potential, the picture will change a bit. So certain, these states will shift in energy according to the local value of the external potential. And we see that states near the edge will become either occupied or will cease to be occupied, assuming that there are near the edges states that lie close to this Fermi energy. Right. So if we can now convince ourselves that, you see, there are these states close to the Fermi energy and living near the edge, and moreover that if I occupy these states by an electron, this electron will automatically move along the edge in the required way, then we will have solved this awkward issue of charge build-up, because then we have a mechanism for this charge to flow away along the edge, and that is what we want. Right, so that is the qualitative picture. So now how should this behave in order to correspond to this equation here? So we want that if some spectral window of edge modes delta is occupied, then is completely occupied by electrons, then we want these electrons to carry an edge current proportional to the Hall potential and the size of the energy window occupied. Why is that? Because the window of newly occupied edge states is precisely equal to the value of the external potential there. And so by the statement just made, if that is true, then it follows that precisely the bulk current, the electrons dumped on the edge by the bulk current are transported away by the edge current. So another property of these edge states that I have here posited to solve the problem is that merely by being occupied, they will, so if you occupy these states with an electron localized at a point somewhere, then this electron will automatically move with the correct velocity. And such a dynamics, basically a one-dimensional dynamics where you have a particle moving automatically without any external driving or whatever, it acts a bit like a conveyor belt, that should correspond to absolutely continuous spectrum of the Hamiltonian. Sort of, if you, right, so it could certainly not be pure point spectrum, because of course if you occupy a pure point, an eigenstate of the Hamiltonian, then it will not move at all. So the converse of that statement, which is not really a theorem, but in any case, spectrum that when you occupy it leads to ballistic motion, we expect it to correspond to absolutely continuous spectrum of the Hamiltonian. So the intuition being given, let me now briefly state the theorem. So I will model a Hall insulator by a single particle Hamiltonian H in the bulk, so to speak, so on an infinite lattice set 2. And I assume it to have a spectral gap, which makes it an electrical insulator. And I assume this material to be such that it is a non-trivial Hall insulator, so that it indeed has this Hall conductance in the bulk. Then I will take the same Hamiltonian and restrict it to a half plane. So a half plane has an infinite edge, and so there we expect to see something that corresponds to the foregoing story. And then the theorem is that if this bulk system has a non-zero Hall conductance, then indeed the insulating gap, where the Fermi energy lies in, if you restrict the bulk system to a half plane, this gap will be completely filled by absolutely continuous spectrum corresponding to these edge states that are responsible for carrying away all the charges dumped on the edge by the bulk phenomena. Since I only have 2 minutes left, I think I will gladly skip the proof, and thank you for your attention.
Thank you very much. Do we have any questions? Seems not. I think online we didn't have anything else.
Could you show the statement again?
So I must admit, I haven't really defined all the quantities in the statement. It's a very impressionistic statement of the theorem, but it is what it is.
Can you say something short about the proof?
Yes, sure. Right, so the proof does not follow the physics story at all, actually. So one celebrated fact in this whole business is the bulk boundary correspondence, and you can associate very nice topological indices to both this bulk system and the boundary system. And these topological indices are already proven to be equal to each other. So the bulk index is the bulk Hall conductance, and the boundary index is constructed as follows. You construct a unitary from the edge Hamiltonian as shown here, and it takes this form. It's the exponential of 2 pi I f of the boundary Hamiltonian, where f is a smooth function interpolating from 0 to 1, whose derivative is supported in the bulk gap. So you see that the only states that really play a role in this unitary, where this unitary does not act as the identity, are precisely these edge states. And in fact, what this unitary will do is it will move stuff along the edge. So what the bulk index is then simply defined as how much stuff does this edge unitary move along the edge, and that is measured by this trace here. So you take all the states sitting to the left of some line, cutting the edge in two, and you ask if I move all those states by this edge unitary, how much will I have moved in total? And that number turns out, in fact, to be an integer and equal to the bulk Hall conductance. But it can be, okay, it follows from the result of H, Poisson, and Joie that a unitary with such a non-trivial index equal to the Hall conductance is equivalent actually to the shift raised to the power of this index, which is the bulk Hall conductance, plus trivial things up to a trace class perturbation. But the shift is well known to have absolutely continuous spectrum. Absolutely continuous spectrum is stable under trace class perturbation, so our edge unitary has absolutely continuous spectrum over the whole unit circle. And then, okay, you stare at the definition of U, and you see that this more or less immediately implies that the edge Hamiltonian H tilde has absolutely continuous spectrum there where the function f has a non-zero derivative, which is precisely in the bulk gap. And that concludes the theorem. Oh. Yeah, let me show the theorem to end.
So this is for non-periodic.
This does work for non-periodic systems, yes. Okay. Well, for periodic systems, it's almost trivial, right? Because they use Bloch transform. If you have periodicity along the edge, you use the Bloch transform. And the only way not to have absolutely continuous spectrum is if everything collapses to a point or something, but that's highly non-generic.
Okay, good. Well, thank you very much.
Thank you.